Hello friends, here in this video we will see a problem which is based on diesel cycle. Let us get started. I'll write whatever is given in this problem in the form of data. Now calculate the percentage loss in the ideal efficiency of a diesel engine. So by reading this question we can understand that since it is a diesel engine, it will work on diesel cycle. So I'll write down that the type of cycle is diesel. It is diesel cycle. Calculate the percentage loss. So we need to find out that percentage loss in the ideal efficiency, that is percentage loss in efficiency of a diesel engine with compression ratio of 14. So compression ratio is R, or I can say R suffix C, that is more specific. Compression ratio is 14. If the fuel cutoff is delayed from 5% to 8%. So in first case the fuel cutoff is at 5%, and in the second case the fuel cutoff is 8%. So there is a delay, as we can see. At first the duration of fuel cutoff is less and now the duration has increased, so there is a delay in the fuel cutoff. And if there is this delay in the fuel cutoff, we need to find out how much would be the percentage loss in efficiency for the diesel cycle. So with the data understood, let us try to get the solution to this problem. Now in the solution part, first thing I will do is draw the PV and TS diagram for diesel cycle. So here I am drawing the PV and TS diagram of a diesel cycle. In that, first we'll start with PV and then TS. Now in the PV and TS diagram we need to know the processes, so I'll write down the processes that take place in diesel cycle are, the processes are, first is process 1 to 2, that is reversible isentropic compression. Next, process 2 to 3 is constant pressure heat addition. Then process 3 to 4 is reversible isentropic expansion. At last, process 4 to 1 is constant volume heat rejection. So now if we see here, these are the four processes which take place in case of diesel cycle, and these four processes we have to show on PV and TS diagram. So the first one is process 1 to 2, reversible isentropic compression. Now this reversible isentropic compression is shown on PV diagram with the help of process 1 to 2. So this is the isentropic compression process, wherein as we can see the volume at point number 1, which is V1, is greater and the volume at point number 2 is smaller. So during the compression process volume decreases, but there is a rise in pressure from P1 to P2. Next, constant pressure heat addition. So the pressure remains constant during the next process and heat gets added from 2 to 3. So here I can see that P2 is equal to P3. Then process 3 to 4 is reversible isentropic expansion. So in case of expansion, the curve is same like it was in compression, but the volume was decreasing in compression. During expansion, the volume increases and the process is 3 to 4, which is reversible isentropic expansion. Next, process 4 to 1 is constant volume heat rejection. So the volume remains constant from 4 to 1, that is V1 is equal to V4. Now I can say that process 1 to 2 and 3 to 4, they follow the law PV raised to gamma is equal to constant, which is for reversible isentropic process. During 2 to 3 pressure is constant and during 4 to 1 the volume is constant. Next, I'll show the processes on TS diagram. First one is isentropic expansion. So it will be shown with the help of a vertical line from 1 to 2, that is isentropic process, wherein as we see here the entropy remains constant, S1 is equal to S2, and the temperature is increasing continuously from T1 to T2. So process 1 to 2 is isentropic compression process. Next, 2 to 3 is constant pressure heat addition. So here I am drawing a constant pressure line, P is equal to constant, and during the heat addition process temperature should increase along this line but pressure should remain constant. So I'll mark here point 3, that is during 2 to 3 the pressure remains constant but temperature goes on increasing and we get the highest temperature as T3. Next, process 3 to 4 is reversible isentropic expansion. That will again be shown with the help of a vertical line, but the temperature drops here. So temperature has dropped from T3 to T4 and here the entropy remains constant, that is like during compression the entropy remains constant, S1 is equal to S2. Similarly during expansion entropy remains constant, S3 is equal to S4. Then during process 4 to 1 it is a constant volume heat rejection. So here I'll draw a constant volume line, and when heat is rejected at constant volume the process should follow this line. So we are following the line from 4 to 1, which indicates constant volume heat rejection. Next, I can say that during 2 to 3 the heat is added, Q suffix A. During 4 to 1 heat is rejected, Q suffix R. Then work during compression, that will be W suffix C, work done into the system, and work we are getting from the system, that will be W suffix E, work we are getting during the expansion process. So this is the PV and TS diagram for diesel cycle. Next I'll see what to solve or what we have to find out in this question. So now once we have completed the PV and TS diagram, Here, if we see in the question, we had to find out the percentage loss in efficiency, and the first condition is fuel cutoff is at 5% of stroke. So here I'll start with this. I'll say that it is case number 1. That is fuel cutoff ratio is 5%. So now what we are going to do, that for fuel cutoff ratio is 5%, we will find the efficiency of diesel cycle. So now I'll say that after this, since the fuel cutoff ratio is at 5%, this 5% is of stroke volume. Here we have to remember that the fuel gets cut off during the duration, or the duration which is given as 5%, it is 5% of stroke volume. So now therefore the fuel cutoff ratio, I'll say that during the PV and TS diagram, we can see that the fuel has been injected at point 2, that is here the fuel addition starts, and it gets completed at point 3. So V2 is equal to V3. Here as I see, during V2 the fuel addition starts and up to V3 it continues. So V3 minus V2 is the duration during which the fuel gets injected. So therefore I'll say that V3 minus V2 is the volume up to which the fuel gets injected, and then the swept volume is from, I can say that V1 minus V2, because V1 is the cylinder volume, V2 is the clearance volume. So from cylinder volume, if I subtract clearance volume, I am going to get the swept volume, which is V1 minus V2. So this is equal to 5% of stroke volume, which is nothing but V1 minus V2. Next, therefore V3 minus V2 in the numerator, I'll send V1 minus V2 on the left hand side, and that is equal to 5%, which is 0.05. Now here what I'll do is, therefore dividing here the numerator and dividing the denominator by V2, and that is done for some purpose. So therefore here in the numerator we have V3 minus V2, so we are going to divide this by V2, and even the denominator, which is V1 minus V2, will be divided by V2. So here I am dividing both numerator and denominator by V2, that is equal to 0.05. So I can simplify this. This V2 will go to V3 by V2. So therefore V3 by V2 minus, here we have V2 upon V2, next in the denominator we have V1 by V2 minus V2 upon V2 is equal to 0.05. Now if we see here, V2 upon V2, it will get cancelled out, so here 1 remains. Similarly in the denominator, V2 gets cancelled and 1 remains. Now Therefore V3 by V2 can be denoted as rho minus 1 upon V1 by V2 can be denoted as R suffix C, compression ratio, minus 1, and that is equal to 0.05. Here into the bracket I will mention that since rho is called as fuel cutoff ratio and fuel cutoff ratio is volume after cutoff to the volume before cutoff. So we have rho is equal to, now if we see in the PV diagram, the volume after cutoff is V3 and before cutoff, that is where the fuel injection starts, that is V2. So V3 upon V2 is the fuel cutoff ratio. And similarly RC is called as compression ratio and RC is compression ratio, which is equal to cylinder volume upon clearance volume. And here as I can see, the cylinder volume is up to V1, clearance volume is up to V2. So V1 by V2 is the compression ratio. Now this I have mentioned in the bracket. So therefore rho minus 1 upon RC minus 1. Now RC compression ratio is given in the problem. We have written in the data. RC is 14. So rho will remain as it is. Rho minus 1 is equal to, here we have 14 minus 1 is equal to 0.05. So therefore rho will be 0.05. 14 minus 1, that is 13, it gets multiplied here. Minus 1 when it comes onto the other side becomes plus 1. So I am getting the answer of rho as 1.65. Now once I know the answer of rho, I can calculate the efficiency of diesel cycle. So therefore efficiency of air standard, because diesel cycle is also called as air standard cycle, so air standard diesel cycle is given by, the formula of efficiency of diesel cycle is, it is 1 minus 1 upon gamma into bracket, it is RC raised to gamma minus 1, then into the bracket it is rho raised to gamma minus 1, in the denominator we have rho minus 1. So here is the formula to calculate the efficiency of diesel cycle. Now I'll go on putting the values here. Therefore efficiency of diesel is equal to 1 minus 1 upon, now gamma for air we can take the value as 1.4, it is the standard value. RC is given in the problem as 14 raised to 1.4 minus 1. Now rho value we have found out, it is 1.65. So 1.65 raised to the power 1.4 minus 1 upon 1.65 minus 1. So here I'll write down, assuming for air gamma is equal to 1.4. So therefore on calculations here I'll get it as, here 1 minus this term is 0.248 into the term inside the bracket, which is 1.563. So from this I am getting the efficiency of diesel cycle as 0.612, or when I multiply it by 100 it becomes 61.2%. So this is the efficiency of diesel cycle which we are getting from the first case. I'll give it as equation A. So now for case number 1, that is fuel cutoff ratio is 5%, we are getting efficiency of diesel cycle as 61.2%. Now I'll use the case number 2. So case number 2, that is fuel cutoff ratio is delayed up to 8%. That is, we have to take the fuel cutoff ratio as 8%, which is the second case. Now for this case also I can say that previously, as we have solved for case number 1, I'll solve it for case number 2 as well. That is, the fuel cutoff takes place between V3 and V2. So V3 minus V2 will be on one side, is equal to, this fuel cutoff is at 8% of stroke volume. So therefore V3 minus V2 is equal to 8%, that is 8 by 100, and stroke volume is V1 minus V2. As we can see it from the PV diagram, V1 minus V2 is stroke volume. So therefore we have V3 minus V2 is equal to, now 8 by 100, that will be 0.08. This V1 minus V2, when it gets shifted onto the left hand side, here we have V1 minus V2. So now therefore I'll divide the numerator and denominator both by V2, as I have done for case number 1. So therefore here we will be having V3 upon V2 minus V2 by V2, that is in the numerator, and similarly we will have V1 by V2 minus V2 by V2 in the denominator, that is equal to 0.08. So in the numerator V2 upon V2 gets cancelled out, so 1 remains. Similarly in the denominator V2 by V2 gets cancelled out, 1 remains. So therefore V3 by V2, I'll write it as rho minus 1, and V1 by V2 is RC, compression ratio, minus 1 is equal to 0.08. I'll mention that since rho is equal to fuel cutoff ratio, which is V3 by V2, and RC is equal to compression ratio, and that is equal to V1 by V2. So now therefore I'll keep rho here, so rho minus 1, RC minus 1, RC is 14 given, minus 1 into 0.08. So therefore rho will be here, this is 13 into 0.08 minus 1, when it goes on to the other side it becomes plus 1. So therefore the value of rho, it comes out to be, it is 2.04, the answer which I have. Now after getting the value of rho, next thing would be I'll calculate the efficiency of diesel cycle like I have in the first case. So therefore efficiency of diesel cycle is given by, the formula was efficiency of diesel cycle is equal to 1 minus 1 upon gamma into bracket RC raised to gamma minus 1 into bracket rho raised to gamma minus 1 upon rho minus 1 . So therefore here I'll go on putting the values. 1 minus 1 upon gamma is 1.4, RC is 14. Next, value of rho, it is 2.04. 2.04 raised to 1.4 minus 1 upon 2.04 minus 1. Here assuming for air gamma is equal to 1.4, called as adiabatic index. So therefore the efficiency of diesel cycle, here I have the first term, it comes out to be 0.248 into the term inside the bracket, that is 1.647. So from this I am getting the efficiency of diesel cycle as 0.591, and if I multiply by 100 I am going to get it as 59.1%, keeping this as equation number second, or equation B I'll say. So now we can closely understand that in case number 1 the efficiency was 61.2%, that is when the fuel cutoff was at 5%. Next, in the second case, when the fuel cutoff is at 8%, the efficiency has decreased. So I'll write down, therefore percentage decrease in efficiency is given by, that percentage decrease in efficiency will be equal to, during case number second, or we can say here during case number second the efficiency was less, and in case 1 the efficiency was more. So 61.2 minus 59.1, so therefore the answer comes out to be 2.1%. This is our final answer. So hence we can say that if there is delay during the fuel cutoff, then the efficiency of diesel cycle will decrease. So here is the comment which I have written, that when we increase the fuel cutoff, that is if we delay the fuel cutoff, that in this case it was 5% to 8%, so the efficiency of diesel cycle decreases, and with this we complete the problem.